Thank you, Martin. Like Marge, I would first like to thank the organizers for the kind invitation and also the three gentlemen for providing the occasion. What I will be talking about is really something about regular polyhedra, but then also a lot about the ways to generalize these objects to combinatorial structures which are highly regular. Whenever we talk about regular polyhedra, the first thing that comes to mind are the Platonic solids. So I'll speak a little bit about the history and how these polytopes appeared through ages. And the person who is credited with being the first, who is responsible for the proof that there are no other but the 5 regular convex polyhedra is Theaetetus, who was a contemporary of Plato. Plato wrote about the Platonic solids, or as we now call them, the Platonic solids, and they played a prominent role in his philosophy. The work of Theaetetus, of course, appears in the book 13 of the Euclid's Elements. However, the knowledge of the Platonic solids predates the Greeks by many years. So about 5,000 years ago, we had carved stone bowls which exhibit the symmetries of the Platonic solids. So in this particular picture here, now I'm trying to, we have the 3 solids, each one based on the octahedral symmetry. So some of these carved stones really appear as either the regular solids or somehow connected with the symmetries of these regular solids. However, not all of them appeared. To date, there was thousands of these carved stone bowls found. But to date, none is found that resembles the icosahedron, as far as I know. These bowls have been found in the northeast Scotland, majority of them in Aberdeenshire, and most of them are now located in the British Museum. The non-regular but the very highly symmetric convex polyhedra have been enumerated by Archimedes. Now, none of his work survived, but it is mentioned in the work of Pappus of Alexandria. Then we come to Renaissance, and Piero della Francesca is perhaps the most responsible for introducing the mathematics in the illustrations in the Renaissance. Piero della Francesca is best known for his paintings. However, he did translate from Greek to Latin some of the work of Archimedes, not on the semi-regular solids. And he also wrote some of his own work listed here. He was particularly interested in the perspective of paintings, but also in the regular solids. Here is a painting of the ideal city. Many of these paintings exist, but this is the one which is kept in the Urbino. Some people attribute it to Piero della Francesca. However, it's also attributed to Lucian Vragnanin and Fra Carnevale, but also to others as well. About the same time, Luca Pacioli wrote a book which was quite influential, quite well known in his days, the Divina Proporzione. And in this book, he illustrated many polyhedra, which were drawn, in fact, by his close friend, Leonardo da Vinci. In around 1550, Giorgio Vasari wrote a biography of Della Francesca and claimed that much of the book plagiarized the unpublished manuscripts of Della Francesca. He was correct because some of these manuscripts have been discovered recently. As I said, Luca Pacioli was quite well known, and here is his portrait by Jacopo de Barbari. Jacopo de Barbary is a fantastic painter, but this is one of only 12 remaining of his paintings. Sometimes later on, not in the original paintings, the portrait here was added, which is most likely that of Albrecht Dürer. Jacopo de Barbary was in Venice for a while. He left Venice in about 1500 for Germany, and he is credited with introducing Italian Renaissance to Northern Europe. In fact, he and Albrecht Dürer knew each other. And here is, of course, one of the quite well-known engravings of Melancholia I by Albrecht Dürer. Another form of art that deals with polyhedra and also appeared in Renaissance is Intarsia. Intarsia are mosaics made with inlaid wood. And here you have a picture of two of such, so they are two-dimensional, they are mosaics. This is one in the Church of Santa Maria of Organo in Verona, and it's credited to Fra Giovanni de Verona. All of those images of polyhedra were based on that book by Luca Pacioli. And then we have, or I couldn't find any for a very long time, but some of my favorite form of art that involves polyhedra are the mirrors, the kaleidoscopes, which can be two of them. They're kind of human size kaleidoscopes. They can be found in the Museum of Science at UNAM, National University of Mexico in Mexico City. They were made by an artist, Juan Sandoval, and designed by the mathematician Rolly Braccio. I took these pictures looking through one of the windows of the kaleidoscope, and you can see here the people walking on the museum. You can see in the background, in fact, the beautiful tiles, also made by Juan Sandoval. They are Penrose tilings, beautiful. So I recommend that if you happen to be in Mexico City, definitely go visit the museum. The mirrors is what influenced the early work of Coxeter. He was fascinated by mirrors. In fact, he himself designed both icosahedral and octahedral kaleidoscopes and had them built in a workshop in London. I inherited them from Donald Coxeter, and very recently, because they were deteriorating, they were used in classrooms at York University, I donated them to the Canadian Institute of Science and Technology, which is currently closed but will reopen for 150th anniversary of Canada. And I hope they will exhibit these mirrors. I donated a bunch of other polyhedral models of Coxeter to the museum as well. And as written here, Coxeter really is responsible for the revival of interest in polyhedra and polytopes, and also for the most comprehensive treatment of the subject. So let me start with the enumeration. Of course, these are the 5 Platonic solids. So I'm first looking at regular polyhedra with convex faces. So the finite ones are the only finite ones are the Platonic solids, and each one of them can be described by a Schläfli type. For example, dodecahedron has pentagonal faces, 3 meeting at each vertex, which we refer to as the vertex figures. So the vertex figures are the triangles. However, we can have regular polyhedra with convex faces which are not finite. And in fact, it was Petrie that was a school friend of Donald Coxeter in 1926 that was very excited when he discovered 2 of such regular polyhedra. He immediately wrote to Coxeter. Coxeter was extremely excited and immediately discovered a 3rd and the only other possible infinite regular polyhedron. So here are the pictures of these regular polyhedra. They're Each of them is related to the cubic tessellation of Euclidean space. As I wrote down here, Petrie was a son of the famous Egyptologist Sir Flinders Petrie and his wife Hilda. To go a little bit to sidetrack from here, when I gave last November, I was at the University of Calgary. I gave 2 talks. This is just a little comment for the birthday gentleman. I gave 2 talks, each 1 hour long, with an hour in between for a coffee. And Richard Guy, who I believe, Ted, correct me, was 100 at that time, stayed, of course, for both talks, had lots to say about both talks, spent the time with me with a coffee, and told me how he taught Petrie. And I said, well, Richard, Petrie must have been older than you. How did you teach? He then told me, I never knew this, you cannot find almost anything about Petrie, the younger Petrie. You can find lots about his father if you Google him. Apparently, Petrie was a school teacher. He never finished university. And then when he was in his 40s, decided he had to remedy this. He went to university, and Richard Guy was his teacher. So it was very nice to learn that little bit of trivia. So let me move on with the regular polyhedra and now consider those with the non-convex faces or non-convex vertex figure. So these 2, the first 2 objects here have star pentagons as faces, and these 2 other ones are their duals, and their vertex figures are star convex polyhedra. Again, their Schläfli symbol can be used for describing them. So pentagram, 5 of them meeting at each vertex, etc. And the first 2, in fact, the ones with the star faces, were discovered by Kepler in 1619. In 1809, Poinsot rediscovered the Keplers too, and then he also discovered their duals. So he was the first one to know all 4. This list is complete. And in 1812, Cauchy proved, in fact, that this list is complete. However, the star polyhedra predate Kepler by number of years, as can be seen here in a marble tarsia on the floor of St. Mark Basilica in Venice, and it's an early 15th century, due to the early 15th century. In 1970s, Branco-Goen-Braun decided that there was something odd about the definition of regular polyhedra, and he restored the symmetry into the definition of regular polyhedra by saying, well, if Coxeter and Petrie want to consider as a regular polyhedra those objects that have skew vertex figures, we should really allow faces to be skew as well. And so that was in 1970. So for example, here I'm showing you an example, a very simple example of a regular polyhedron with regular skew faces. So we have hexagons on the cube here, which are going to be faces of our new polyhedron. And it's easy to see that, for example, at this edge, you can place such 2 skew polyhedra, and in fact at every vertex you can place 3. So if you look at it as a combinatorial object, you have hexagons, 3 meeting at each vertex. So in fact its Schläfli symbol is 6-3. However, if you just write it as 6-3, that describes the infinite tessellation of the Euclidean plane by regular hexagons. So this 4 here is making it more specific, making it finite. Then of course one can do this in an infinite way, so it's very easy to see that if you take every second vertex in this Petrie-Coxeter infinite polyhedron, and you take the vertex figures at each one of those, you're going to have a regular polyhedron with the skew hexagonal faces. 6 of them will meet at each vertex in a convex manner, so the vertex figures are convex, flat, if you wish. Polygons. And then, of course, one should also allow infinite faces as long as they are regular. And so here is an example which we commonly, it was invented by Branko-Grünbaum, but we now refer to them as being one of the Grünbaum-Dress polyhedron. It will be clear in a minute why. So you take on every fourth square of the cubic tessellation of the plane a stack of cubes, and on each of those stack of cubes you inscribe a helix. You have to make sure that you start vertices at the right spot. And then you connect them with these bridges. So then there are helices going up and down, left and right, and back and forth. So its Schläfli symbol is infinity for the helix, and 3 meeting at each vertex. So this now brings me to a more general concept, and then I'll try to explain as why we call those other polyhedra regular, what is so specific about those polyhedra, because so far I only spoke about geometric polyhedra. So I'm now sort of switching the gear and defining for you very briefly what an abstract polytope is. I will talk about any rank. We're mostly interested in rank 3, but we'll talk about any rank. It's a partial order set whose elements are called faces. It has a strictly monotone rank function which satisfies the following properties. There is a minimal face which you can think of as the empty set, and the unique maximal face, which is the whole polyhedron, so that's a technical thing. The maximal chains, that is the flag of polytopes, always contain exactly n plus 2 faces. It's a strongly flag-connected object, so if you have some sort of a tessellation on a surface, you don't want to make to have a pinch on that surface. That's what really is the consequence of being strongly flag-connected. And we also have something that we refer to as homogeneity property, which is, for example, saying that if you have a vertex here and a face, a polygon, there will be precisely 2 edges that belong to both. So that's kind of a property that's responsible for really making it look polyhedral. We will say that such an abstract polytope is regular if its automorphism group is transitive on the flags of P. So what does that mean? That means that if you take a flag and its adjacent flag, for example, at the level 1, then there will be, being transitive on the flags, there will be an involution which interchanges the 2 flags. And you can, of course, do that at every level, so that the groups of abstract polytopes are generated by involutions, which can be described by this Coxeter diagram. That is, every node represents an involution. They are connected by an edge labeled with the order of the product of the corresponding generators. So when they're not connected, like for example, row 1 and row 2, that means that the order of the 2 generators is 2. The product of the order of 2 generators is 2. So every regular polytope, abstract regular polytope, has as its symmetry group a Coxeter group with a linear diagram. So I wrote that down this in general. So if you have an abstract regular polytope, it's going to be generated by these involutions, and the Coxeter graph is associated with this string Coxeter group, so that in fact to that group you can associate a Schläfli symbol for the polytope. It's also interesting that the generator satisfies certain intersection property. I won't even go into details. It's a very simple property. But why this intersection property? It's because that property, together with the Coxeter diagram, characterizes the groups of abstract polytopes. So quotient of a string Coxeter group with the generators that satisfy the intersection property is called a C group. And then in 1982, Egon Schulte proved that given a C group, one can always construct a regular polytope which has this group as its automorphism group. So it completely characterizes this. These 2 properties characterize the groups of abstract polytopes. So this is a rank 3 example. If you take Euclidean tessellation of the plane by the squares, and then you take a quotient of that group by translation subgroup, you can construct a regular polytopes or maps on a torus of Schläfli type 4-4, as an example.
But this is still abstract.
Still abstract, yes, definitely abstract. I'm going to get back to real soon. You have to bear with me, and it's right here. So, what is the geometric polyhedron? That's a discrete faithful realization of an abstract rank 3 polytope. And you say that it's geometrically regular. If it's symmetry group, that is the group of isometries which keep the polytope invariant, or the polyhedron invariant, is transitive on the set of its flags. So it's very easy to prove that the faces of geometrically regular polyhedron must be regular polygons. And of course, this is the list of all regular polygons. What can they be? They can be convex regular polygons, star regular polygons, skew, or helices, regular helices, or in fact, a flat zigzags. So having the whole list, Branko-Grünbaum, of course, knew that these were the only possible faces for regular polyhedra. He then proposed that he had a complete list of these regular polyhedra. So, there are Platonic solids, the Kepler-Poisson polyhedra, and then there are P-trials and similar some others. And then there are the three Petri-Coxeter polyhedra and 9 exceptional, which we now call Grünbaum-Dress polyhedra. So Grünbaum had a list of 47. He missed one. In 1985, Dress found the last one and proved that the list is complete. Okay? So those are the geometrically regular polyhedra, the list of all geometrically regular polyhedra. Well, now we sort of make the next leap. All right, so the first leap was going to abstract polytope theory. So now we go into the next. We look at something called the incidence systems. An incidence system is a 4-tuple such that X is the set whose elements are called the elements of gamma of the incidence system. I is the finite set whose elements are the types of them, of these elements in X. So we have a type function. To each element, we associate its type. And we have the binary relation, which is called incidence, which is reflexive, symmetric, and has the property that if X is incident with Y, and they have the same type, then they must be equal. So the incidence graph of gamma is the graph whose vertex set is X, and two vertices are joined if the corresponding elements are incidents. It's very easy to see that this is not necessarily a partial ordered set. However, you can still assign rank to such an object. That is the cardinality of I. A flag is the set of pairwise incident elements of gamma. So here is an example. You look at the cube with type 0 elements being vertices, type 1 elements being edges, type 2 elements being the faces, like the blue one in front here. Then the vertex A and the blue face here form a flag. And an element is incident to a flag if it's incident to all elements of the flag. And then we can define the type of flag as the set of all types for a flag. So here we have type 0-2 flag. And then if you take a maximal flag that is of type I, then that's called a chamber. So in this example here, if you take a vertex A, the blue face, and for example, this edge, which is incident with A and the blue face, that gives you a chamber. An incidence system is called the geometry or incidence geometry if every flag is contained in a chamber. So if you, for example, take a cube with all these three different types of elements, vertices, edges, and faces, you append, say, an edge to one vertex, an additional edge to this vertex, you're going to get an incidence system, but it's not going to be a geometry. we're particularly interested in the objects, it will become clear why, which geometries which are called thin. And the geometry is called thin if for each I the flag of type, all elements in I except I, is contained in exactly 2 chambers. So here is our previous example. If you take flag consisting of the blue face and vertex A, then there are precisely 2 chambers which this flag is contained in. So this thinness is very much resembling the property which I called the homogeneity property. You know, given a vertex and a face, there are precisely 2 edges, etc. So, in fact, that the polytopes are examples of thin geometries. Clearly, it does not work the other way around. So, a thin geometry is not necessarily a polytope. So, as I said, the homogeneity condition definition of abstract polytopes guarantees that abstract polytopes are thin geometries. Non-degenerate maps and hypermaps are also examples of thin geometry. So maps are abstract polytopes of rank 3, but hypermaps are not. I'll give you an example in a bit. So now we define this next generalization of the concept of polytope. We call it the hypertope. So hypertopes to polytopes are what hypermaps are to maps, if you wish. So a hypertope is a thin incidence geometry that's strongly chamber connected. So again, we don't allow those pinches. A hypertope is said to be regular if the group of its automorphisms, actually we have to be a little bit more specific here, it has to be type-preserving automorphisms, has exactly 1 orbit on the chambers. So it's a chamber transitive. And then it's very easy to see, well, not too difficult to see, that if you have a regular hypertope and you fix one of its chambers, then for each type I, there exists an involution, which type-preserving involution, which interchanges flag with its adjacent chamber with its adjacent chamber. So that means that the group of regular hypertopes, again, is generated by involutions. So, in fact, one can show that the type-preserving automorphisms of an thin incidence geometry is always generated by these distinguished generators, involutions. Given a fixed flag, you can always do this, which will satisfy relations implicit in a Coxeter diagram, but now it's not going to be necessarily linear. So we now think of this the Coxeter diagram for this group will be a complete graph on n vertices. So the vertices are again labeled by the involutions, and again you connect the 2 vertices by an edge which is labeled by the order of the product of those involutions. And if you don't connect it, just think of it as being an edge which is labeled by 2. So the groups of regular abstract polytopes again are C groups generated by involutions. In fact, they're not that, they're quotients of these groups, to be more specific. And they also satisfy intersection property, very much like the one that we had in the case of polytopes. So, given a pair of a group and the set of relations, which is generated by a set of involutory elements, which satisfies this intersection condition, again we call a C group. But the corresponding Coxeter diagram is not linear. We keep that in mind. So here's an example of a hypermap. So the hypermap is going to have these blue vertices. Let's call those blue objects vertices. So they are type 0 elements. Type 1 elements, type 2 elements will be these blue faces. And type 1 elements will be these white hyper edges. All right, so a hyper edge has 3 vertices on it, and say this hyper edge is adjacent to 3 hyperfaces. All right, the Coxeter diagram for this group, in fact, is this triangle here. It's not linear anymore. So that's an example of a hypermap, a simple one. And so as we constructed polytopes from C groups, so quotients of Coxeter groups with a linear diagram that satisfy the intersection condition, the question is whether we can do something like that for hypertopes. Can we construct these? Because they're hard to kind of visualize except in rank 3. So this construction, in fact, is based on the construction of an incidence geometry that's due to Tits, 1956. If you take a group and the finite family of subgroups of that group, then if you define the set of elements as the set of all, say, right cosets, these indices will be defined what you call a type, and then you say that the 2 are incident if and only if the intersection of the cosets is non-empty, then you in fact get, as Tietz proved, an incidence system. So the question that we wanted the question we asked and wanted an answer to was, when is such an incidence geometry a hypertope? In other words, a regular hypertope, really. So we also looked at other types, not just the regular, but for the purposes of this talk, I want to talk about the regular hypertopes. So when is such an incidence geometry a hypertope? In 2014, Maria Elisa Fernandez, Dimitri Limans, and myself proved that, in fact, for rank 3, the question is not too difficult. So if you have a group, what did I do now here? I jumped way ahead, sorry. If you take a group generated by 3 involutions, then the corresponding coset geometry with these 3 subgroups, which are called the parabolic subgroups, but I don't want to go here in the details. So you take these 3 subgroups where you always omit exactly 1 generator from the group to get the subgroup, is thin if and only if it acts faithfully on G and it's transitive on chambers. So in order to check whether you have a regular rank 3 hypertope, all you have to do is check thinness. Unfortunately, it wasn't so easy for the higher ranks, and it took us quite a long time we tried to prove that this is working for any rank until we came up with counterexamples. And then we realized that if you have a group which is generated by n involutions, so it's a C group, it satisfies intersection condition, and it's a quotient of a Coxeter group, then the coset geometry is going to give you a regular hypertope if and only if you have flag transitivity or equivalently chamber transitivity. So you have a little bit more checking to do in the case of rank above 3, higher than 3. Let me just say a few words. Okay, let me go back here and say, so what the geometers, at least the geometers in the area where I work, want to do is we come up with all these theories, and then what do we want to do? We want to enumerate, all right? I mean, there you have a Coxeter enumerator, Grunbaum enumerator, we're all enumerating. So then we wanted to do some enumeration of these hypertopes. Now, if you look at the spherical hypertopes, yeah, sure, you can enumerate them, but all of their groups are the finitely reducible Coxeter groups. Well, all you can do is you can plug this into Magma or something, and you can eventually list everything. So we didn't bother with that. It can be done. It probably should be done, but maybe by a graduate student. Anyhow, so we said, okay, well, let's look at if we can enumerate regular hypertopes on a torus. And in fact, already in 1948, Donald Coxeter was interested in that sort of thing. So he wanted to enumerate regular maps on torus. So, of course, what he did is he takes a regular tessellation of the Euclidean plane, and then he factors it by a translation subgroup. And then, according to that, can classify what he called the regular maps, but they could be what we nowadays call regular or chiral. The regular maps have only one orbit on the flags. The chiral maps have precisely two orbits on the flags with specific properties. But that's what he called the regular. So that's what's actually written here. And so he proved that of type 4-4, you can have only these two families of regular maps on a torus of type 4-4. For type 3-6, you can have another two families. And then for type 6-3, which are the duals of 3-6, all you have to do is look at the duals of these two families and you get there. So how do you construct these regular maps? Well, you essentially do what teats, the construction of teats. So you look at the maximal parabolic subgroups, you look at the vertices are fixed by rho 1 and rho 0. You look at orbit of all those objects, you get vertices of your map, and similarly for the other things. And now we double the fundamental region, and what you get is a hypermap. As you double the fundamental region, the linear group generated by R0, R1, and R2 now will be generated by the three involutions, keeping R1 and R2, dropping R0, but taking the conjugate of R1 by R0. And that's how you get a hypermap. So then now these have been introduced by Sigerman, but also classified as well for the torus. So now what do you do in general? So you start with the Euclidean tessellation. You know what it means for it to be regular. You have flag transitivity. And then you can easily see that these are the only regular tessellations in Euclidean spaces. You can have a cubical tessellation in every rank greater than 2, and then 2 exceptional in rank 2 and in rank 4. And in fact, the symmetry group of these tessellations are precisely the infinitely reducible Coxeter groups of Euclidean type with the linear diagram, like these red ones that I listed here. So if you take the group of all translation at G, its symmetry group, you take a subgroup which is generated by n independent translations, you can get a toroidal polytope by factoring the translations by this subgroup. And that is the definition of the toroid. And as an abstract polytope, a toroid is an abstract polytope. The faces are the orbits of I faces of the tessellation, and similar for the flags. So we just denote that whenever you have a subgroup lambda generated by a vector S, and then take all its images under the point group of that group, then we describe the corresponding, or denote the corresponding polytope by T sub S. In 2002, Macmillan and Schulte gave the classification of regular toroids, all regular toroidal polytope. They proved, of course, Coxeter already know that for n equals to 2, you have precisely 2 of those. But for higher ranks, I'm sorry, I'm rushing. For higher ranks, you always have 3 families, which are described by these parameters. They also did a classification for rank 6, so everything is classified. So the only regular toroids are the ones listed up above. This is how they look like. So I will just skip this picture. I can come back to it if you wish. So our next question is if you can bear with me for another 3 minutes. Martin, can I have another 3 minutes? Okay. We wanted to classify toroidal hypertopes. Well, then we used the analogous construction for the toroidal polytopes from affine Coxeter groups with linear diagram, but now our diagrams need not be linear anymore. And so this becomes a much more difficult question. We of course know that regular hypertopes will be regular polytopes whenever their diagrams are linear. So you saw an example of a toroidal hypermap I gave you earlier on. And so we look at now what can happen in rank 4. So in rank 4, there is only one affine Coxeter group with linear diagram, and there are two with a nonlinear diagram, so these two. As luck would have it, both of these are subgroups in the group with the linear diagram, so that made the work possible. As I mentioned earlier, the classification of regular hypertopes with linear diagrams, that is regular polytopes, was completed by McMullen and Schulte. And this last year, Eric Anskis, my PhD student, proved, or rather found the classification for all of them for regular hypertopes of rank 4. And they are given with these parameters for both of the families, so for both of those possibilities. That you don't want to know. So I will just end with a few open problems. Classification of regular toroidal hypertopes in rank greater than 4. I'm working on that with Egon Schulte and Dimitri Liemans. We have some partial results, but it's not complete. So that's still an open problem. Existence of chiral toroidal hypertopes. So these are very highly regular hypertopes which have two orbits on the flags, and Donald Coxeter used to call them regular. Somerville called them regular as well. Existence of such in ranks greater than 4 is an open problem. McMullen and Schulte proved there are no toroidal chiral polytopes in rank greater than 4, and Eric Hans proved that there are no toroidal chiral hypertopes in rank 4. Otherwise, the problem is open. A big open problem is the classification of locally spherical hypertopes. I'm working on this problem as well with Dimitri Liemans and Maria Elisa Fernandez. We have quite a few partially answered problems. We have resolved some of the possible families. By the way, this problem dates back to 1970s and the questions asked by Branko Grimbaum. But again, this is incomplete. And then, of course, something that will be very interesting to solve is the classification of uniform polyhedra. So as you probably know, the uniform polyhedra with planar faces have been enumerated by Coxeter, Logan, Higgins, and Miller in 1954. The ones with the non-planar faces, a number of examples have been found by Abby Williams, but the question is still completely open.